vector bundles. This is a joint work with my postdoc supervisor, Diane McLagan. So what is rank R vector bundle? Rank R vector bundle on a space, say on a scheme, you can think of in two ways. So it's a space together with a map to X. This is in the sense of geometric vector bundle. So the fibers are vector spaces. Locally, it has a trivialization, and it will look like product of r-dimensional vector space. So this is called trivialization. So this is some attaching some linear algebra object to a space. So it is parameterizing vector space over the points of the variety or the underlying space. And these are transition functions. So these are from intersection of two open sets to GLR K. Equivalently, these objects are usually think of as locally receive of OX modules. So vector bundles are important object in classical algebraic geometry. So it is natural to consider the tropical counterpart. So the story of higher rank vector bundle on tropical varieties was started by Alderman in 12. He considers tropical vector bundle on tropical cycles. So his definition is in the spirit of geometry vector bundle. So he gives a nice cover over which it is locally trivial, and the transition maps are some piecewise linear object. Then Gross, Ulidis, and Zakharov considered vector bundle on tropical curve. Okay. I missed one board. So, sorry, can I write here? So they have considered vector bundle on tropical curve. Or metric graphs. So this is dimension one situation. So in higher dimension, in Severing scheme theoretically, this has been studied by June Minseva, Tolliver, 24. So they have considered vector bundles, tropical vector bundles on tropical toric varieties. Tropical toric schemes. More generally, some nice Severing scheme. And they studied in a SIP theoretic way, and the classical correspondence between geometric vector bundle and locally free SIP holds in this setup of semi-module over semi-ring scheme. But the problem here is the following. So in the situation of A, in nice spaces, or nice spaces, say simply connected, vector bundles are trivial. And in the situation of C, it has been shown that all vector bundles are direct sum of line bundles. So all vector bundle splits. So like Horrocks-Mumford's criteria kind of thing, but we don't want all vector bundle to split. So why the main issue is, so usually the transition functions land in GLRC, but if you consider the naive tropicalization of GLRC or GLRK, this is too small. Uh, this is just diagonal. This is just matrices with each column and row contains only one non-zero element. So we have restriction on transition functions that makes all vector bundle to split. So what will be the remedy? So our motivation is to take help of the commutatrix of the toric vector bundle. So look at the commutatrix of toric vector bundle. And we try to use the combinatorial description to get a definition of tropical vector bundle. And what we observe is that, so we need to tropicalize the fibers as well. So for vector bundle, the fibers are vector space. What we want is actually tropicalize the fibers. So our goal will be to get fibers as tropical linear spaces. So let me quickly recall toric varieties. The toric varieties are a combinatorially defined object. Fix a lattice and consider the dual lattice. And we have a torus. This is an algebraic torus. So K is a field. So if I start with a rational polyhedral cone in inner, so for example, if I consider the cone generated by 1, 0, 2 minus 1. So from a cone, we can consider the dual cone. So this is the usual dual. From this dual cone, we obtain a semi-ring, semi-group. And this gives the affine toric variety. By taking spec of this semi-group. So this is our affine toric variety. So what will be the key points of this affine toric variety? So these are elements of K algebra homomorphism. From A sigma to K, but this is same as semi-group homomorphism. From the semi-group S sigma under addition and K under multiplication. So this doesn't depend on the field. So this will help us to tropicalize affine toric variety. Now we go to tropical affine toric variety. We can tropicalize this description, and instead of K, we'll take the usual tropical semi-ring. So here R bar is R union infinity with addition and multiplication. I will consider the minimum convention. So this has been first studied by Kajiwara and Penn. So let's look at some example. So in one dimension, if we consider just one ray, so this corresponds to affine line A1 in the toric setup. Now, trough A1 is R bar. So I am considering K together with evaluation. So this will look like the ray. So now, similarly, we can tropicalize the A2 also. And how to get a toric variety? If we start with a rational polyhedral fan sigma in inner. So fan is just a collection of cone. So we can do the gluing to obtain toric variety. And similarly, we can glue the tropical affine toric varieties, and I will get tropical toric variety. So, for example, consider P1. So P1 is given by this fan in R. So this is two rays generated by E1 and minus E1, and the corresponding tropicalization will be the interval. So more generally, tropicalization of a projective toric variety is homeomorphic to the associated polytope. So this is the how we tropicalize toric varieties. I have one more thing to recall. So toric variety comes with a Cox ring. So if the number of rays, if we denote by S, the Cox ring is a polynomial ring in S many variable, and we have tropical Cox ring. So we consider the replace K by R bar, and this is a polynomial ring, but these variables are graded by some, these are A1 class group graded rings. So these are important because we can describe any sheaf on a toric variety as a A1 sigma graded module over the Cox ring. So now we want to tropicalize toric vector bundles. This is the class group of the toric variety, the class of divisors. And in case of toric varieties, we have this short exact sequence. So any character lattice will give a tuple MVI, where Vi are the primitive element of the rays. So now our aim will be to tropicalize toric vector bundles. The toric vector bundle is a vector bundle over toric variety. So toric variety comes with the action of a torus. We want the action should to lift on the total space, and the action preserves the linear structure of the fibers. And what is good about toric vector bundle? So they have a nice combinatorial description. So which is given by Kiyashko. So if we start with the toric vector bundle, rank R toric vector bundle. So these correspond to this family of filtrations. We look at the fiber over the identity of the torus, and we get a decreasing filtration. Full filtration goes to E to 0, and these are indexed by the rays, and they satisfy certain compatibility condition because it's a vector bundle. So this Kliashko reduces an algebraic geometric objects to a bunch of combinatorial data, a bunch of vector spaces indexed by the rays. So, and we denote this data by this. So, for example, if you consider P2, these are the three rays. So, tangent bundle have the following filtration. So, tangent bundle will look like this. So, this is a rank 2 vector bundle. So, we have rank 2 vector space for all j less than equal to 0, and at the place of 1, it will be span of the ray itself. It is one-dimensional vector space, and 0 set 0. So we get a bunch of subspaces. Now, Diophantous-Smith associated a matroid to a toric vector bundle, where they have captured this data of the filtration in a nice way in a matroid. So around 80s, to a toric vector bundle, they have associated a realizable matroid. Let's say G is the ground set. So this is this nice property that all intersection of these subspaces appearing in the filtration occurs as a flat of this matroid. All intersections of EIJs are in the lattice of flats of the matroid. What was the ground set? Yeah, I'm not telling you the ground set. So yeah, there is a way to get the ground set. It's basically start with the one-dimensional pieces appearing in the intersection of the filtration. Okay. So and then they have some algorithm, you add the complementary ones. Okay. So wait, but what if the situation doesn't have a one-dimensional? Then you have to you have a smaller dimensional subspace. You put basis from that subspace. Yeah. So it's basically the idea comes from old work of Dillard. So which is around 73. So basically consider the intersection poset. So take all intersection of EIJs and consider the intersection poset. So this is actually a lattice. So Dillard's algorithm says you can always embed a lattice inside a geometric lattice. So which will be lattice of flat of some matroid. So we also already proved this result in our paper, and to note that so the matroid associated to Turing vector bundle is not unique. So this is not unique, but this agrees with the philosophy that if you want to tropicalize a variety, it depends on the embedding. So when you tropicalize a Turing vector bundle, it will also depend on the choice of the matroid. So from this description, we can uh, tropicalize Turing vector bundle as follows. So you can simply take tropicalization of a Turing vector bundle is the underlying matroid with this choice of this ground set and the filtrations, which can be think of as a lattice of flat of this matroid, and the compatibility condition will automatically come. So, somehow we have used the commutatorics of the Turing vector bundle to tropicalize Turing vector bundle. But the question, so these we call realizable tropical vector bundle. Yeah, vector is it will depend on the choice. So yeah, but the philosophy, as I mentioned, so when we tropicalize a variety, we consider some embedding. The tropicalization somehow depends on the embedding. So here also the tropicalization will depend on the embedding. So I will talk about the dependence later.
Yes, there is a fully matrix that's unique.
Sorry.
I think there's a fully matrix that's unique. Maybe.
Yeah, actually, there is a way to associate a unique matroid also with some minimal condition. We can associate some unique matroid, but that is not helping to get some properties of the vector bundle, which I will come later. So now, what is the geometry of algebra or algebraic analog of this tropicalization? So for this, we consider the Cox module description of a Turing vector bundle. So yeah, so line bundle, it will have a matroid with one element because we are considering loopless. So it will be just ground set will be one element, and we will have filtration. So it will correspond to bunch of integers. So for line bundle, the filtration will be like this. So this will be the integers, and this corresponds to the usual piecewise linear function. The line bundle corresponds to piecewise linear function. So these are the integers.
And so it corresponds to a Taurus equivariant line bundle.
Yeah, and all line bundle are cross equivariant. So,
but the choice of the Taurus
yeah.
method. Yeah. Okay.
Yeah, I'll take a toss equivalent structure, then I will get the integers. So if I have a Turing vector bundle, we have this matroid data. So this helps to get a surjection onto this Turing vector bundle from a direct sum of equivariant line bundles indexed by the entries of the ground set. So these are equivariant line bundle, and this is an equivariant map. So somehow we get an equivariant presentation. So this surjection will see the matroid as follows. So if you look at the fiber level, so there are many elements. So call m the number of elements in the ground set. So we have surjection to the fiber is a r-dimensional vector space. So what we get is there is a linear subspace L of Km such that the fiber over torus is actually identified with this cosine. So this gives the matroid structure on the fiber. So more precisely, we can see this toric vector bundle E as a simplification of a finer graded Z power sigma 1 graded S is the Cox ring P. So where P encodes this data. So we shift this by some integer. So I'll define what is dw. So for each w in the ground set, this is an element S tuple. So this basically captures the data of the filtration. So this is maximum over all j, such that this w is inside Eij. And we have submodule cosine by a submodule R. This R will capture the linear dependencies appearing in the matroid. So in this way also, we can now tropicalize toric vector bundle. So we replace the Cox ring by tropical Cox ring, and this is think of as a linear dependency relation. We homogenize this relation and take the Bain congruence. Let me write it down. So before that, consider the example of the tangent bundle. I have just erased. So the tangent bundle has this filtration. One-dimensional vector space. Here, the ground set will consist of these vectors. And DWIs will be just standard basis vector in Z3. So Z3, because we have 3 rays. So in this case, P will look like this. So S is the Cox ring in 3 variable. So we'll shift by and the matroid is on these elements. So there is only one circuit E1 plus E2 plus E3. We homogenize the circuit. So this is the Cox module description, and we can tropicalize just by replacing S by tropical Cox ring. This is shifted by DWs. And here we consider the Giant-Saragossa-Bain congruence. We have a more commutal way of tropicalizing, and this is more module theoretic way. So this will motivate us to define what is called tropical toric bundle. One description is just can be think of as a abstraction of Kliachko classification. So this is it. We can take more generally valuated matroid. Because we can, in the realizable case, we can give a valuated structure on this matroid on a ground set, and we specify a chain of flats in the lattice of flat of the underlying matroid, and we put some abstract compatibility condition so that it behaves like a vector bundle. And similarly, we can tropicalize this Cox module description. So tropical vector bundle is a simplification Jetpa sigma 1 graded this module of the form so we start with a matroid, we have a ground set. So we'll have some integer dw, and here grow modulo by Bain congruence of homogenized circuits of M. But so there are vector bundles which will not come as tropicalization of toric vector bundle. So if we start with a non-realizable matroid, for example, so this is enlarging the class of tropicalized toric vector bundle. So we can there are example non-realizable tropical vector bundles. So for example, if you consider the phenomatroid, on the ground set of 7 elements, from this matroid we can get a tropical toric vector bundle. So we consider this fan This consists of 7 rays. This can be think of blow up of feasible surface. So there, so this is not realizable when its characteristic defined from 2. So we get a rank 3 vector bundle on X sigma. We have to specify the filtration. So I'll specify 2 filtration, how it will look like. We'll take the flat 1, 2, 3, 1 and empty set. And similarly on E2, I want to take G 2, 4, 6, 2 set. And similarly on other rays. And we have to check the compatibility condition and this satisfy the compatibility condition. So in our definition, this gives a trophical toric vector bundle, but of course this cannot come from a realizable matroid. So there are more vector bundles. So now we want to study the property of these vector bundles. So like decomposability, splitting property, and what will be the space of sections. So first consider splitting property. So we have a notion of a direct sum of matroid. So you can define when a tropical toric variety will split. So if the underlying matroid splits as direct sum of rank 1 matroids. But so it shows that tropical. So classically, Grothendieck's result says any vector bundle over projective line splits. We have analogous tropical Grothendieck result. But so we consider tropical projective line, but some nice, we have to put some condition, some modularity conditions. Plus some minimality condition. Then such a tropical vector bundle on tropion splits.
Is it an artifact of the proof, or is it not true that that you need conditions, or is it not true that any tropical vector bundle?
No, it's not even only like we cannot drop these two conditions. If you drop, we have counter example. So it appears that if we're studying this type of properties of tropical vector bundle, the modularity in the lattice of flat is playing a big role here.
But once they split, they're always realizable, right? So is that sort of realizability that
Once they splits,
I mean, you essentially have like features in your functions in the
yeah, but we have some example where the matroid is realizable, but we are taking the which lattice of flats. These are not coming as realizations. So there are two-way the
But if
realizability
the
can
bundle
break.
is direct sum of line bundles, then I mean, is every line bundle realizable in your world?
Yeah, every line bundle is realizable.
So then it's direct sum of those. So shouldn't that be what's realizable, or am I?
Um, Okay, I haven't
Okay,
thought that. Yeah, I'll. So this is about the splitting criteria. So similarly, we have a notion of a global section. What will be global sections? So we have this vector bundle. So motivated by Dirac, Jabo, Smith, we can still associate a bunch of polytope indexed by element of the ground set. So these are elements in the dual lattice. Or on I. Yes. So we get a bunch of polytopes. So using this, we can define the rank of the global section. So this is rank of the space of global sections. So sum of rank of its weighted decompositions, where it dimension of the weight space is defined as rank of which of those elements W, where U is in PW. So this is again just motivated from the combinatorics.
So this is
Sorry.
always finite,
Uh,
even if the equation is not proper?
No, we are taking complete actually. More generally projective. So we can and this definition matches with the tropicalization. So namely, if we start with a tropical vector bundle, the rank of the global section will matches with its tropicalization. So in a sense, at least this definition is compatible with the usual tropicalization. And finally, I want to talk about the another property of stability of vector bundles. We were able to define some notion of stability of this type of bundles. So if we were motivated by the following result, that if you have a toric vector bundle. Okay, so before that, what is stability? Stability is a property of vector bundle. So to a vector bundle, we associate some slope, some rational number, and we say E is stable if for all subshifts, the slope of all subshifts is strictly less than E. So for all, if subshift of E, and similarly semi-stable if the inequality holds. So on a toric vector bundle, we have shown in our earlier paper with Dasgupta that saturated So if a Turing vector bundle comes with this data of a filtration, then saturated equivariant subshifts. So this corresponds to just subspaces of E. Because from a subspace, we can naturally induce a filtration. So this from this we can identify what subshift, like sub-object of a tropical toric variety you want to consider. So defining stability as follows: if E is a tropical toric vector bundle, so for each flat in the lattice of flat, we can associate a tropical toric vector bundle, which we call as our subshift or sub-object, and we can associate it a slope. So we can compare them. So in this way, we are defining a notion of semi-stability. Again, to some extent, this behaves well under tropicalization. Yeah, actually, I'm taking algebraically closed characteristic 0, and also here the toric variety is also projective. So we have this reason. Actually, so if F is a toric vector bundle, which is stable or semi-stable, then its tropicalization also preserve stability and semi-stability. But if toric vector bundle this is unstable, then there exists a choice of tropicalization. Which is unstable. So it seems if we choose a correct tropicalization, then nice properties will behave well. And finally, so if we assume some more extra modularity assumption,
Is it defined only for certain saturated subsheets or for any subsheet?
in tropical world. So actually in tropical world, we are so a tropical vector bundle comes with a matroid. We have the lattice of flats. So for each flat, we are associating a subsheet. We will consider only those subsets. And yeah, at least for if we start with the Turing vector bundle, in this definition, tropicalization, stability of tropicalization behaves well. And also, if we assume some more modularity assumption on the lattice of flats involving the flats EIJs, then we are able to construct the usual Harder-Nordsen filtration and Jordan Holder. Yeah, with some more assumptions, we were also able to prove this filtration is unique. So these are basically reduces the study of a vector bundle by semi-stable vector bundle, and Jordan-Holder filtration reduces the study of semi-stable vector bundle by stable vector bundles. So I'll just so this is the story about tropical toric vector bundle. But our next question is which vector bundles we can tropicalize. Vector bundle and any variety y. How do we tropicalize? So if the following condition holds, if y has a embedding inside some toric variety, and if we start with the vector bundle y, if there exists an embedding and a toric vector bundle f on x sigma, such that this pullbacks to this original bundle, then we are only able to tropicalize. But unfortunately, this holds for very ample line bundle, but we don't have a good class of examples for which this type of properties holds. So next step would be to try to tropicalize more general bundles like this, other than toric vector bundles. Thank you. I will stop.